Alrighty. You should all be able to hear me. I believe. Yeah, the microphone says you can hear me. Cool. So today we're gonna go over the quiz that you guys had last week. Or Monday, I think. Anyway, we're just gonna go over it real quick. So the first question asks, why do we need to know calculus to understand physics? She's almost always gonna ask something like this because she wants you guys to understand that Newton created calculus for physics. As long as you put something like that, she'll be pretty content. Examples include you need to like derive expression, derive velocity from displacement or from acceleration, or integrate to get it from acceleration. She just wants you to understand that these derivations that we're doing are calculus. And the reason that we can explain the motion of these particles is because we have that calculus to go from displacement to velocity to acceleration and backwards and forwards and all that. So we basically want to put Newton created calculus for physics. Something along those lines, and you'll pretty much get those points. So now we'll go on to the actual math. This one says, given the position of her cat, and she added a little photo of her cat, which I found was really cute. The cat runs 5 seconds to catch a mouse. Calculate displacement. All right, that one's pretty easy. That one is just plugging it in, right? Into the displacement, because that's x, which is our displacement. Cool. And then I'm gonna type this one so that it goes by a little faster. So then we have x after 5 seconds is equal to 0.75 meters, and then I'm leaving space. I'll just leave a space there because it's hard to do the meters over second cubed in Zoom. It's 1.323 meters over second squared. Leaving space for that. Plus 4.21 meters over second probably too. Time was 0.67. And then I'm just going to go ahead and draw in our units because you do want to write those when you're solving this. Cube, right, seconds cube, times cube. That's going to leave you with meters. That checks out in terms of units. And then meters over second squared. Note that because you see this meters over second squared, you know that this could end up being the acceleration based on the units, and it would not have a t because the units are already where they're supposed to be. But this one, you would still have a t there if you were to drive down into acceleration. The reason I say that is because you have, right, meters over seconds cubed. Acceleration is meter over second squared. So if you wanted to derive this down to acceleration, you would still need a t to cancel out that second in the units. So then I think all the other units are there, right? So then you just plug in 5. This t cubed becomes 5 seconds cubed. T squared becomes 5 seconds squared. It's pretty, just plugging it in. Little squiggle down your seconds. I'm trying to make it definitely noticeably smaller than the 5 because I know I sometimes write the 5 and the seconds that they kind of look the same. All right, so then you plug all that in. And you should get, sorry, let me just do this in my calculator. I'll do it little by little so that you guys can see. 93, 3.75 meters plus 30.75 meters. 0.05 meters. And right, we should all be in meters because the time would have canceled out with the inputting of time squared or cubed. Means x to 5 seconds is equal to meters. So then we'll just go ahead and double check that with P. Right. So you see I made a mistake here. I just did displacement. I did sorry. I did not do displacement. I did location after 5 seconds. And then because this is location after 5 seconds, then we need to understand that displacement is delta x. Right? So that means that this needs to be minus t naught. So x to the 5 seconds minus x to the 0 seconds would equal to 146 point minus 0.67 meters. And that would equal to 145.55. Cool. Remember that when t is equal to 0, keep that. That means that all these things that you would plug in for t is equal to 0. So if this was 0, then that would become 0. If the t was 0, then it becomes 0. T was 0 seconds. That section would become 0. And because this doesn't have a t, it doesn't become 0. So let me do that in text again. 0 plus 0 plus, these should be meters. I should include the meters in there. I believe that's it. Because you plugged in t for 0 and all of those. And that leaves you with 145 meters, which should be the same as the key now. Yeah. Nice. So then it asks us to derive an expression for Gigi's velocity. So I'm gonna go ahead and erase some of this. I'm just gonna keep the formula here for displacement, because from the displacement formula, we can derive our velocity. I'm gonna remind you that to do this, we're gonna use the power rule. Oh, too far. I'm gonna go ahead and move this whole thing up a bit. A second. There we go. So then for average velocity, it would be is equal to delta x over delta t, right? That's for average. So then for instantaneous velocity, we're gonna do dx over dt. Let me make that a bit clearer. For average, and then instantaneous velocity is the d version. Let's put that inside. To b is equal to dx. I'm gonna go ahead and make that v is little v because it's a big V like that in physics usually means like volume or volts. We got a little V because it's flow setting. You guys don't need to worry about that. I just want to be correct. So then, right, to turn this into V, we are going to do power rule. So that means that 3 from the T is going to come down. And we'll multiply it by the coefficient that's already there. Keep the units. I'll just leave space for the units for the T. 2 times units. That's 1 times. And then this is gonna be 2, right? Because we subtracted that 3 by 1. Squared. This t squared is going to become t to the power of 1. And then this t is just 1. Because t to the power of 0 is equal to 1. Obviously, that's a 1. And then you put that up here. Then in case you didn't follow, it's this t minus 1. Then 3 comes out and puts itself right there. Same thing here, the 2 is going to come out, put itself right there. And then you're going to subtract by 1. This is an imaginary 1 up here. You're going to take it and put it down there, and subtract by 1. Oh my gosh, this Zoom's being funky. There we go. Sorry about that. Two. 2.25. Some space for the meters in t squared. I'm gonna go ahead and mute because I'm in the media center and they're being a little loud, and I'm not sure if you can hear them. Or right, so then this became by simplifying it, by multiplying. We'll take care of C later. Let me make sure you guys know we're doing B. And then from here, I'm gonna do acceleration because it's the next obvious thing. And then we'll go back and do C later. remember that acceleration is equal to change in v over the change in t. In this case, we're doing instantaneous and finding an expression. So we're going to do dv over dt. Right, so we did the power rule, which then moved this 2 from this t and turned that t into a regular t. Probably should have just written that t, it looks pretty small there. And then this t becomes t to the power of 0, which is equal to 1. As I mentioned before, this one was probably just going to end up as acceleration without t, because you have those meters per second squared unit. And then this one just becomes 0, because you imagine a 0, t to the 0 there, and then that just kind of cancels out. Right? So then if we simplify from here, we have acceleration is equal to 4.5 meters over seconds to the third power. That's what that caret is, times t plus 2.46 meters to the second power. Cool. And then D is asking if acceleration is constant, which no, it is not constant, because you have that t right there. Let me just move some stuff up. It is not constant because it is still a function of t. So then as t changes, acceleration will change. That just means it still has a t variable. That's what function of t means. And if you were to write it, it would look like this: a t. Well, I'm just gonna go ahead and circle the t so you guys can see. Right, because we still have this t here. Function of t. Cool. So then that means we did A, we did B. We skipped C so that we could do D and this one. Let's explain the units derived. Right, so for velocity, this makes sense because, let me do this in the color. This 3 is gonna cancel out by this 2 seconds, and that's gonna be left with 1. This second squared, there's gonna be a seconds to the power of the 1 up here. It's gonna leave you a second over 1. And then this is kilometers over seconds, so velocity meters over seconds, and that's what you see in your equation. And that's basically just what you want you to check that, yeah, the units make sense, because that's what you expect for velocity. Same thing for acceleration. You have a t to the power of the 1 here, which that's going to cancel out from this 3 and leave it with 2. And then you have power and meters over second squared, which leaves you with meters over second squared for both. This is 0 you can just kind of ignore. And that's what you expect for acceleration. That's all she means by explain the units derived. So from there, let's do C. I'll underline this so you guys can know what the colors mean. So average velocity means that we're going to use this equation, right? And so then you have intervals t0 and t5. We calculated displacement earlier, where I erased it, but x to the 0 seconds was 0.67 meters. I could probably actually just type this. It'll be easier to see. Is there a way to make this text smaller? I guess not. 0.67 meters. Why did it do that? X to the 0 seconds to 0.67 meters. Next to the 5 seconds was equal to, I believe it was 145 point something. Let's just check it. Or 5.5. So then that means we can just plug that into the velocity equation. Here and add this into there. You have delta x Here's delta t. Let's do this with the text box, which is x to the 5 seconds, right? Because this is our bigger number, bigger in terms of what occurred last in terms of time. It's minus 0 seconds. Then that's equal to, or it becomes 145.55 meters. Note that you could have or might have rounded here before changing it. That's valid, but I like to do things unrounded just to prevent any round errors. Oh wait, that's already the displacement, isn't it? Yeah, that was already displacement. So I believe this was yeah, we had already found displacement. Because delta x to the 5 seconds was 146.22 meters. And then we subtracted that by x to the 0 seconds to solve for displacement, which is what that is right there. So then from there, we just need a delta t, which is 5 seconds minus 0 seconds, since that's your t naught. It's basically 5 seconds. Then 145.55 divided by 5. So 29.11 meters over seconds, which if I were to guess for rounding would become like 2.9, sorry, 29.1 meters per second. Cool. And then I believe that was all the parts of quiz 1. We can go ahead and double check our answers with the answer key, if we can see through. Let me move this. Oh, we can't. Anyway, displacement is 145 meters, 145.55, yep. And then our velocity was, make sure I'm doing the pointer thing. Can we see velocity here? Yeah, our velocity is up here. Our velocity up there. Do this in red. Then we have the 25.5 meters over seconds, which is correct. We have it right here. Before we did it, turned into acceleration. And then we have this, or right here. And this one right there. This one became that one. This one became that one. It's just that they, after multiplying, they look different. And then check units is meters over seconds. This is what you wanted to see right here. Cool. And then, yeah, the average velocity was 21.1 meters per second squared. Check. Acceleration. This is here. Then this is our acceleration, which is right here. and it is the same. Alrighty. And then acceleration is dependent on time, because it is a function of t, and therefore is not constant. Just about the same thing. And then acceleration is meters over second squared. Check, we got that too. Spec. Alrighty, so now that we've gone over quiz 1, we're gonna go over there we go. Chapter 3. These are just some things that I noticed that we've done so far. We've done a lot of vector components. She told you guys to make sure your calculators are in degrees so that you get the right answer with the trigonometry. Then she expects you to know like how you add and subtract vectors and some trigonometry, which is useful for finding the x and y components of vectors. So we have, this is just some trigonometry review. We have SOHCAHTOA, which let me type it up here. SOHCAHTOA, where sine is opposite over hypotenuse. Cosine so is equal to opposite over hypotenuse. That's 0. Pi is equal to adjacent over hypotenuse. And TOA is equal to opposite over adjacent, or, oh, this one is equal to sine. Cosine, sine, tangent, or tan. Cool. And then that's just basically what this is telling you here. All right, if your angle is theta here, then the sine opposite is B, and the hypotenuse is always the opposite from the 90 degrees, because this SOHCAHTOA is only for 90-degree angles. Cosine, then this one is adjacent right next to it, and then opposite over adjacent is B over A. Cool. I guess something else that would be useful is remembering that this is the same as sine over cosine. And that's because, oh my gosh, I'm not draw a circle here. Never mind. Sine theta over cosine theta. And the reason for this is that they'll basically cancel out. Because right, we have sine over cosine. Sine is opposite over hypotenuse. And then cosine is adjacent over hypotenuse. Right. And then that's gonna equal to opposite over adjacent. which is tangent. I had someone ask me about my method of doing this thing right here. Because what I usually do is I do brackets for the center two and the outer two, because that's what makes sense for me. There are two ways of doing it, really. You can also do the inverse, and then the inverse of 1, which is hypotenuse over adjacent. From there, these two hypotenuses cancel out. That equals to opposite over adjacent. For me, this is counterintuitive because the way I remember to do the inverse is by dividing it by 1, and then doing the brackets. So that's why I usually do this thing, the outer 2 with the inner 2. And that becomes opposite times hypotenuse over adjacent times hypotenuse. And then the h's still cancel out to give you opposite over adjacent. There might also be other ways, but that's just what I remember. This is also shown by this image over here with the unit circle. Because you have cosine on the x direction, sine on the y direction. That's useful, especially for if you're dealing with like 90 degrees or 180 degrees, because you know that if it's 0, you can imagine, okay, if theta is like 90 degrees, then that's 0 along the x-axis. Also, then cosine would be 0 because cosine is x, and little reasoning like that helps. I know someone memorized like all the little 60, 45, 30 degrees. Those could help you, but you'll always have your calculator, as far as I remember, so you'll be fine. And then again, tangent is like sine over cosine, and this is just like a visual representation of how that looks. I'm gonna go ahead and clear my drawings. So then we'll start with our first problem. This one's relatively simple. You have a delivery truck that travels 228 blocks north, 16 blocks east, and 26 blocks south. I'm gonna go ahead and take a screenshot of this, because I feel like we'll be right better there. To take a screenshot, by the way, to Shift Windows S. Let me make sure I'm screen sharing everything. And the reason I did it is because it has a here. So let's do this. So I'm defining, oh, that is way too big. But it's never eat soggy wafers or waffles for your directions. This is still kind of big, so let me turn this. There's a way to rotate this. I'm usually doing this on my computer. Alrighty, never mind. This is redundant since I can't seem to rotate the ruler. That's fine. So I'm just gonna do, that's about 28 blocks. And we're gonna go 16 blocks east. So let's do 16, 28. And then we're gonna go 26 blocks south, which is short of 28. It asks for final displacement from the origin. Thankfully, this is all in X and Y values, right? Where let's define our axes over here. We have X horizontal and Y vertical. And then we'll do the never eat soggy waffles again. I do recommend you know how to draw a little compass, because sometimes we'll do north and south values. So you're just going, I would believe that's clockwise. Never eat soggy waffles. Cool. So then in our X direction, I'm gonna number these. So we have A, B, and C for our vectors. And they should have little arrow hats with them because they're vectors, meaning they have a magnitude and direction, right? Your magnitude is this block, the number of blocks, and your direction is whether it's north, south, east, west, etc. So then for our X, we only really have one in X when that's vector B. Our Y direction, we have vector A and vector C. A is pointing up, C is pointing down. That means they are opposite to each other and we're going to subtract them. And B is, what is that, left? Right. Right, so seeing as we defined our axis as this is positive direction, then that means vector B is positive. Vector A, which is up and into the positive direction, is positive, and vector C is negative. From there, we're gonna go ahead and just add them. So in the X direction, we have a positive 16 blocks. In the Y direction, we have a positive 28 blocks. Plus a negative 26 blocks. It should equal to like 2, positive 2. Yeah. Cool. So then we can draw our vector, right? We know it's positive 2 blocks. That's 2 blocks. Sorry, wrong way. We can go positive 16 blocks in that direction. And then if we go 2 blocks in the Y direction, so obviously this is not exact scale, then this is our vector here, right? Because these are going this way. And so this is a tail to tip addition method. And because we have it in the x and the y, that's 90 degrees. Then this is the angle you're trying to solve for. I'll do a little theta in red. And then, right, we can also kind of draw that as a resultant vector right here. And the word that I said was resultant. Here. Coolio? So then we have plus 16 blocks. Alrighty, so from here we can do one of two things. And we're gonna have to do either one, so whichever one is first is fine. I'm going to do the Pythagorean theorem first. Which, let me write that over here. Pythag. That might be spelled wrong, Pythagorean. Don't harsh on me. That's just a squared plus b squared is equal to c squared. And I'll add the squared in right now. And that's for right angles, which this is your resultant vector is a right angle. So that means we can use it. This is going to become the square root of a squared plus b squared. Because we're solving for the hypotenuse and we have the a or the x plus the b or the y. We basically have the two quote unquote legs of the triangle. And then we have hypotenuse. Again, I'm sorry if my spelling is incorrect. I'll use some room for the square root. 16. There's room for the square root, or for the squared. Right in. Squared. It's also squared. And all of this is under square root. So then that should equal to square root of 16 squared plus 4, because 2 squared. I'll do it a little. 16 squared. I'm just gonna leave out the blocks because it's kind of long to write. This is 25. 156 blocks. And then this is equal to 4 blocks. Which add those together should be like 260. Right, this is gonna be box squared because you squared it. That x is the box squared, which that will become 16.12. 1, 2. square root is gonna get rid of this squared here. Oh, not this right here. So that's blocks. Cool. So that's your displacement. But if she asks for like a displacement vector, you need this theta here. So this is opposite from the angle. This is adjacent from the angle. And you know, tangent is equal to opposite over adjacent. Because SOHCAHTOA, TOA, opposite over adjacent. And I should have moved this. I always forget to write the theta. Not the theta, sorry. Yeah, not the theta. Remember that to do the inverse, you're gonna do tangent arctangent or tangent to the -1. I'll put that over here. Let's put X. Y and become or let's hope this isn't covering too much. Okay, cool, it doesn't cover anything. It's tangent to the -1. Well, these mean the same thing. So then I'm gonna do the arctangent version just so that we can see it. Or I can type it down. I'm just gonna put angle because you can't put like theta in here. So that means that arctangent opposite is 2, and then adjacent is 16. And then if you plug that into your calculator, on the calculator, it probably looks like tangent to the -1. That's gonna give you 7.1125, which I'm gonna put as 3. And this is usually it's in degrees. Let me make sure that my believe my calculators in degrees, but I'm not sure. I believe it is. If it's not, then it'll just look a little different, but this value makes sense. Because it's relatively small and it is in the positive direction, which both of these are positive, so you're expecting that. And then I believe that is the end of our time. So I hope you guys have a nice day and take care.